Okay, so in the event that you're having to watch this class from home today, we're doing free fall acceleration today and just doing some things about dot diagrams down in the bottom. Okay, so a constant velocity car versus a constant acceleration car. If I were to take a picture of that buggy car, that red car, every second and sort of make a dot where it's located, you would see that the dots are equally spaced. Yesterday, I think most of you measured your speed of that buggy car to be in the neighborhood of 30 centimeters per second, 0.3 meters per second. If that was taken every second, a picture, you would see that those things would be 30 centimeters apart. So every second it travels a set distance. If it's a constant acceleration car, you might have noticed that the fan car started out really slow, and then as time went on, it was going faster and faster and faster. So if I had a fan car, you might see that the dots are increasing in distance. So we can use dot diagrams to indicate whether or not the motion is constant or the motion is accelerated. One of those things has balanced forces. Balanced forces are described by Newton's first law. Which one would have balanced forces? The constant velocity. One of those things require unbalanced forces, and unbalanced forces cause changes in motion. The CA car would have unbalanced forces. Those unbalanced forces are causing it to change its motion. All right, so you're going to see on your quiz on Tuesday, and I'm glad I pushed that out a little bit, because there are some things I just did not do at all. You're going to see that you're going to have to interpret or draw a dot diagram about constant speed versus accelerated motion. Okay, so something like that would be useful to sort of keep in mind. And I think on your review, there's some things there about dot diagrams. Okay, and so you'll see some of that. We'll go over that review on Tuesday if you went through it. Okay, we'll plan again on Tuesday for that quiz. Okay, got to show you a couple of equations. You're not going to see calculations like this on the quiz. It's more for the project. So acceleration examples. The average acceleration is defined as change in velocity over time. If I rewrote that equation for delta v, it would be a times t. And if I solve that for t, it would be delta v over a. Again, you're going to be given equations to be able to use. Sometimes you have to rearrange the equation for a particular thing. True story, my first car was that 1979 Dodge Omni. It wasn't very high performance, but when I graduated college, I finally was able to go and buy a fancy car. And I always wanted one of these things. They looked really cool. It's Mitsubishi Eclipse. And so that could go 0 to 64 in 8 seconds. If I wanted to calculate that car's acceleration, average acceleration, it was also a stick shift, by the way. I would just go delta v over t. 0 to 64 means it went a change of 64 miles per hour, and that took 8 seconds. And if my memory serves on that, that would be an 8. 64 divided by 8 is 8. And then that unit would be miles per hour per second. And so that car could accelerate at more than twice the rate of my first car. Raise your hand, please. You've been to Cedar Point. You've ridden on the Top Thrill dragster before that. Now, it was shut down. I think I was there like 5-6 years ago. And then it shut down after that because they had maintenance issues. And I think a part of the Top Thrill dragster came off during the ride, and it like landed in the area where all the people were lined up. I think someone might have got injured. Yeah, I mean, someone really got injured on that, so they shut it down. And I think they might have is it running again now? Did they redo it or something like that? I'm not sure. Anyways, what's thrilling about it is that it could change its speed really quickly. So it could go 0 to 120. And it could do that in 4 seconds. So what was thrilling about the dragster is not its speed, but how quickly it could change its speed. So its average acceleration is not too bad. A is delta v over t. I would go 120 miles per hour, and I change that in 4 seconds. That's a 30 mile per hour per second acceleration. 10 times what my original car could do. Concept-based question for you. Can you sense motion? Can you tell that you're moving? You really can't. You can't tell that you're moving. As an example, we're moving at about 18 miles per hour, 18 miles per second around the sun. That's how fast you're moving. Our motion around the sun is about 18 miles every second. We can't tell that because it's a constant speed. But you can sense accelerated motion? Can you tell when you're speeding up in the car? Do you feel that? Can you tell when you're slowing down? Yeah. Can you tell when you're turning? You can sense accelerated motion. You can't sense motion. You sense changes in motion. So your body is actually a pretty good accelerometer. It cannot measure motion, it measures changes in motion. The more aggressively you feel like you're pushed or pulled, the more acceleration you're experiencing. All right, this concept-based question. I need someone, you got a truck in your family, you own a truck? Would you mind, Lauren, really quick, what color? Gray? Gray? All right. So we have a truck, and thank you, Lauren, for doing this for me. So there's a gray truck. It can go, it's accelerating from rest to 15 kilometers per hour in 5 seconds. So that's your truck. Anyone have a sports car in their family? What do you have? A Porsche? What color? Red? Okay. So now we have a sports car. Does it have a spoiler on it or anything?
Yeah.
Okay. So we have a sports car. It's going 125 and it's going to accelerate to 140 in the same amount of time. My question for you is, which of these things has the greater acceleration? Concept-based question. See if you can do that for me. Just look at it, share with that person that you're sitting next to what you think that answer is, and then we'll see how we did. Right? So which of those are accelerating at a greater rate? And I'm hoping you see that the delta V is exactly the same. Each of them experiences a change in velocity of 15 kilometers per hour. This one goes from 125 to 140. This one goes from 0 to 15. It's the same delta V in the same amount of time. So they have the same acceleration. As a matter of fact, I would sense if you were in your truck and you felt when you stepped on the gas and it went 0 to 15 in 5 seconds, you would feel a certain kind of thing. You would feel exactly the same as how Liam would feel if he was in 125 and go to 140 in 5 seconds. You feel the delta V. You feel that change in acceleration, or the change in motion. If I were to graph the truck's velocity as a function of time, it would be increasing, going faster and faster and faster. Every second, it would be 3 kilometers per hour per second, 3 kilometers per hour faster every second. For those of you that have that strong math background, that'd be the slope of that line. The red car would have the same slope. It's just higher up on the axis. It starts at 125, it gets to 140. In the same amount of time, it would have the same acceleration. I'm going to not do this one here. We're not going to do that kind of math, and we don't need to spend time on it. So just put a line through that one. Okay. Now, folks, the main topic I wanted to look at today was this thing called free fall acceleration. If I could have got to that yesterday, it would have made sense, but it just ran out of time. So I want to do this one today. It's our main topic, free fall acceleration. The asterisk on it means that you're not going to have to do the math of free fall acceleration on quizzes. It would just be on the project. In the absence of air drag, all objects experience the same acceleration due to gravity. It is independent of the weight of the object. Doesn't matter if it's a feather, a bowling ball, or a truck. They're going to accelerate equally, independent of the weight. It's independent of the size. It's independent of the shape if there's no air drag. Now, we always see air drag acting on objects, so we don't observe this unless we could actually have a specialized condition. Now, this one is sort of hard to do without having a vacuum chamber and stuff like that. So I'm going to show you a video of this. It's from the BBC, so British broadcast channel. And so it's pretty cool what they did. And so you may have seen this video before. If you haven't, it's about 5 minutes in length, and it just shows you what happens to objects when they fall in the presence of without any air resistance. Okay, I don't know how a recording of a recording would do, but we'll try it. You grab the lights for me. This is Really quick, I just got to take a moment. I don't know how much you guys know about atmospheric pressure. Don't know. But what they're doing is they're trying to create like conditions that exist in outer space. No pressure. So a vacuum. Do you guys know what atmospheric pressure is here on Earth? Like what the amount of force per square inch that we feel because of our atmosphere? You know what that is? Something like 14 pounds. 14.7 is pretty close to 15 pounds per square inch. What that means is on every square inch of our body, we have about 15 pounds of force due to the weight of the air, right? If we remove that, like why do they have all these like cautions, like sealed chamber? If you go into that chamber and you don't have that external pressure of 15 pounds per square inch acting on your body is pushing out right now to maintain equilibrium, pushing out with a force of 15 pounds per square inch to keep you in a state of equilibrium. All of a sudden now your body would just explode essentially. Right? So that would be that. So what they're doing is they're pumping out that air. And it takes about 3 hours to remove the air. We don't see the air that's around us. And so that air now is no longer going to be able to interact with those things there. And you should see that they accelerate equally. That's the theory. So it's pretty cool to see this in real life. It's hard to see it in real life because we don't have vacuum chambers around. So it's sort of interesting. These people are all highly trained scientists, and they're still amazed by that. It's sort of cool to see. Unfortunately, it's sort of hard to replicate that. But if you haven't seen that video before, it's pretty cool. All right, Kylie, would you grab the lights for me? So, folks, a little bit of math here. The table shows the rate of speed changes is about 10 meters per second per second. So you notice as I look at this table, every second that this thing falls, the speed, if I had a speedometer on it, the speed would be increasing by about 10 meters per second every second. Now, that's a little bit of an approximation. The more accurate value is 9.8. But for most purposes, we would just use, we would use G to be about 10 meters per second per second. Let me write the more accurate value is about 9.8. In your math classes, you may have used a falling object model that had a 16 in it. You might remember that. That would be half of this value. So if it were in English units, it would be 32 feet per second per second. My personal favorite is the one that involves miles per hour per second. So if I were to take my car 0 to 60 in 20 seconds and push it off a cliff and allow the earth to speed it up, it would change its velocity at about 22 miles per hour per second. What that means is that if the earth were my engine for my car, it would get to 0 to 60 in less than 3 seconds. It would pick up speed pretty quickly. So gravity itself is quite fast. It causes objects to change their motion pretty quickly. We would, if we're standardized on SI units, this is the one that we would use because it's in meters per second per second. If I wanted to find the velocity, I would just take the acceleration due to gravity, which we call g, and just multiply by the time. Now, I think you guys know the speed of your egg drop device is going to play a role in the force that it feels. Would you guys agree with that? The faster it's moving, the more force it's going to have. Let's say that it drops from the ceiling here, and it takes 1.2 seconds to fall. Let's just say that it does. Could you use that with g being 10 to determine about how fast it's going? 1.2, if I multiply by that 10, it'd be about 12 meters per second. Let's say that you drop it off the balcony over there and it takes 2.3 seconds to fall. Just multiply that by G, it'd be about 23 meters per second. One year, when I was feeling ambitious, I took kids out to the field, to the football stadium. The balcony there, the bleachers that face to the north, there's like a huge drop off on that north side. Drop something from there, if it takes like 3.3 seconds for it to land, how fast would it be going? About 33 meters per second. So it's just telling us how quickly things change their velocity. Now, this, I'm going to put a line through that. I'm not going to worry about objects being thrown up and stuff like that. It's just, we have to focus on just the essentials. So I'm not going to worry about that one. Your only thing you have to worry about is if you drop something from rest. So I'm not going to worry about it. Let's move on to this stuff. I want to measure your reaction time today. And to measure that reaction time, we have to look at how far an object falls while it's picking up speed. You might notice that this strobe diagram of a dropped object, the distance value is getting larger each second. So in the first second it falls a certain distance, and the next second it increases, and the next second it increases more. And so this is not a linear relationship. So if I look at this table, I can see that the change in distance, it's no longer going up by a set value. That changes 5. This changes 15. This changes 25. This changes 35. This changes 45. I notice that they keep going up by an increasing value. Some of you might notice that this changes 10. This changes 10. This changes 10. And so that 10 has to do with that acceleration value. More mathematical than a lot of people would care to get into, but that's talking about an accelerated motion. The equation to describe how far it falls is, I'm just going to write it like this, the change in our position again, we write word equations with letters to make it more concise, so we don't have to have a bunch of things around there. Delta y represents how far it falls. It's changing its position. We have a half in there, so that 32 turned into a 16 in your math class when you saw that. And then we see that it's related to the time squared. So you should expect more of a quadratic relationship here.